Welcome to Classwork 8.6, Textbook Section 6.5, Part 2. Today we're going to continue our study of DeMoivre's theorem. So you might recall last class we ended talking about this theorem, that if you have some complex number, z equals r cosine theta plus I sine theta, or r kiss theta, if you raise that complex number to a power of n, you get r to the n cosine n theta plus I sine n theta. Or more commonly, r to the n kiss n theta. So again, this is called DeMoivre's theorem, and that's what we're going to use today. So look at our first example. You can think of your z as the inside number, so 2 kiss 20. And essentially we're going to raise it to the 6th power. So apply the formula, or apply the theorem. 2 to the 6, kiss, 6 times 20. 2 to the 6th power is 64. And then you get kiss, 120. And that would be the answer in polar form. But notice how it wanted to answer it in rectangular form. So to do that, just do what we learned last class, multiply it out. 64 cosine 120 plus I sine 120. You can do this part in your head if you're comfortable, because we know cosine 120, that would be negative 1/2. Sine 120 is root 3 over 2. So that becomes negative 32 plus 32 root 3I. And there's our first example. Going to our next example. So find 1 plus I to the 8th using DeMoivre's theorem. Write the answer in rectangular form. So you have to know that to use DeMoivre's theorem, you must be in polar form. So again, you have to write that down, that this theorem doesn't really work unless you're in polar form. So to do that, we're going to have to take this number and convert it to polar form. So I'm going to draw a quick triangle here, and let's just graph it. So you can go 1 that way, 1 up, because it's 1 plus 1I. And here's our triangle, 1, 1. And now we can see our hypotenuse. Let's do the root of 2, which means that this would be a isosceles triangle, or we can just use our tangent, right? If you're looking for your angle, you can say tan theta is simply 1 over 1. You're in quadrant 1, so theta should be 45 degrees. And now we're going to use this information to convert it. So our z is going to be the root of 2 kiss 45 degrees. Okay, so this root of 2 is coming from the hypotenuse, or your r value, and this angle is being plugged in right there. So that's your kiss 45 degrees. Okay, so essentially we're just converting our rectangular form to our polar form, similar to last class. Now we're going to raise it to a power. So z to the 8th must be root 2 to the 8th kiss. And since you're multiplying by 8, it might be easier to think of this as pi over 4. That might be an easy number to work with. And then 8 times pi over 4. So this would be 2 to the 4th kiss 2 pi. So 2 to the 4th is 16. Let's expand this. Cosine 2 pi plus I sine 2 pi. Sine of 2 pi is 0, so that's just gone. Cosine of 2 pi is 1, so our answer is 16. Okay, now here's where it gets a little bit more complex. It says finding the roots of a complex number. So to do this, we're basically going to do DeMoivre's theorem backwards. So our notes are going to be right here. DeMoivre's theorem for finding complex roots. So there's a couple of things we have to note first. So this is part of the theorem. If z to the n is equal to w, and this is assuming we're in the complex plane, that would mean w has n distinct roots. Okay, so that's going to be our first understanding. So essentially what this means is that if you have some z to the n here, r to the n, and you have kiss n theta, what we can do is think of this as a box, and we're going to apply a root instead of a regular power. So think of it as z to the 1 over n is equal to r to the 1 over n, and that would make this kiss theta over n. And this is what we're going to use to solve these equations here. So make sure you write this down. And the thing that's kind of complex about this is I wrote earlier it has n distinct roots. This formula we found, this is the first root. Right, so this isn't the complete thing. I'm just saying this is how you find the first root. So we'll talk about how to find the other ones in a little bit. For now, let's just focus on finding one. So let's try that first example. It says, find all the complex fourth roots of 16 kiss 120. So essentially we're saying z to the fourth is equal to 16 kiss 120. So we're going to raise this to the 1/4 power. So now we get z is equal to the fourth root of 16 kiss 120 over 4. So now, to apply this, we're going to write the fourth root of 16 is 2. And this will be kiss 120 over 4 is 30. And notice how it says right roots in polar form, which means this is good. That is polar form. So I can circle that. This is the first root. However, it says there are n distinct roots, so which means if this is a 4, that means there are 4 answers. So clearly we're not done. Now the way we're going to find other answers is we're actually going to use this fact about polar roots. There's a really cool fact about polar roots is that if you were to graph them, the roots are equally spaced. So what I mean by that is imagine we were to graph this 2 kiss 30. That would mean we're about 30 degrees up over here, and this is 2. The other roots are going to be equally spaced along here. So one should be about here, one will be here, and one will be here. Right, so here's our first answer, second answer, third answer, fourth answer. So if we think about this logically, the full circle is 360 degrees. There are 4 answers, which means the spacing is going to be 90 degrees apart. And that's what we're going to use to find the other answers. So the first answer, we'll write z equals, was 2 kiss 30. The next answer is simply 90 degrees away. So just add 90. 2 kiss 120. The next answer is 90 from that. So 2 kiss 210. And the next answer is 90 from that. 2 kiss 300. And there is our final answer. And again, the key here is that we can use this cool idea of the roots is that they're equally spaced on the complex plane, and we can use the spacing. So to complete our notes on the right side, on the right, to find other roots, use spacing. So that's going to be 360 divided by number of roots. You might find this familiar from our rose petals or the rose graphs. Very similar idea here. So for here, let's try something similar. It says solve for z, leave answer in polar form. So basically it's the same thing as saying find the 3 complex roots of that number. So immediately notice that the first problem we did, this one, this is already in polar form. This right here is rectangular, which means you have to convert it to polar form first. So to convert it, let's graph it. So negative 4 root 3 is over here, up 4. So there's our triangle, negative 4 root 3, 4. After you do the Pythagorean theorem, you're going to get 8. Here's our angle theta. Some of you might already know that angle, but if not, it's okay. Just do basic trig. Tan theta should be 4 over negative 4 root 3, which means tan theta should equal negative 1 over root 3. Tan theta is negative root 3 over 3. We're in quadrant 2, so it must be 150 degrees. And now we can convert everything. We have our r, we have our angle. So now we can rewrite this as z cubed must be 8 kiss 150 degrees. Now we're going to apply the 1/3 power. So that would be z is going to be 8 to the 1/3 kiss 150 over 3. So z is equal to 8 to the 1/3 power is 2. And that's kiss 50 degrees. And if you're wondering, 1/3 power, it might be easy to rewrite this as a cube root of 8. And now we can see this is our first root. Now to get the other ones, all you have to do is think, well, how many are there? So look right there, this is 3rd power. So by DeMoivre's theorem, there must be 3 roots total. So think about spacing. There's 360 degrees in a circle. Divide by 3. That's 120 degree spacing. So the next answers are going to be 2 kiss. Just add 120. That's going to be 170 degrees. The next answer is 2 kiss, add 120. That's 290 degrees. And there are the 3 roots, or the 3 solutions for this equation.